welcome back for part 2 of this video, where we're going to look at the linear regression model and the pieces that make it up. In algebra, you may have seen lines written in the form y equals mx plus b. So if you remember, that was called slope-intercept, because it contained the slope, which was m, and the y-intercept, which was b. And statisticians do exactly the same thing, but with different notation. So we use y hat, remember that's your predicted y. Anytime we put the little hat on top of variables, it's predicted, equals b0 plus b1x. And b0, b sub 0, is your y-intercept, and b1 is the slope. We know that a change in one standard deviation of x corresponds to a change of r standard deviations in predicted y. Okay, and we talked about that in the last video. Okay, remember that slope is rise over run, or it's the correlation times the standard deviation of y divided by the standard deviation of x. So the formula for the slope of the least squares regression line is b1 equals r times sy divided by sx. What about the y-intercept? So one important fact here is that the least squares regression line must always pass through what's called the mean point. In other words, it has to pass through x bar, y bar. The model predicts y bar to be the value that corresponds to x bar. So if we replace the means into our equation, we obtain y bar equals b0 plus b1 times x bar. And if I solve for b0, we get b0 equals y bar minus b1x. And that's just simply subtracting, and it's x bar. That's just subtracting b1 x bar from both sides. What do the slope and the y-intercept tell us? Well, the least squares regression line that modeled the roller coaster data is speed hat equals 15.6 plus 0.37 times the height. The slope there is 0.37, that's your b1. And this just means that on average, because remember slope is average rate of change, these roller coasters gain about 0.37 additional miles per hour in top speed for every additional 1 foot tall they are. Because again, slope is change in y over change in x. And y here is speed and x is height. So 0.37 additional miles per hour is your speed for every 1 additional foot tall, which is height. The y-intercept, on the other hand, is your b0, or 15.6, and this just means our model suggests that a roller coaster with a height of 0 feet would still have a top speed of 15.6 miles per hour. Remember that in order to find a y-intercept, x has to be 0, and x in this problem is height. So it's basically saying when the height is 0, if I replace this with 0, 0.37 times 0 goes away, and you're left with 15.6 as your speed, 15.6 miles per hour. So a roller coaster with a height of 0 feet would have a speed of 15.6 miles per hour, which is kind of doesn't make much sense. So the y-intercept at times will not be useful to us. And in that case, it's not really useful because you're not gonna have a roller coaster that has a height of 0 feet, right? It wouldn't make it much of a roller coaster. Okay, so we just kind of answered this question. Do you think the intercept in the above example is meaningful and makes sense? Why or why not? And we said no, because roller coasters have hills, loops, etc., so it's not a height of 0 feet. You can pause the video and now try this next problem where you're going to interpret the slope and the y-intercept and reflect on if the y-intercept is meaningful. And then you can unpause when you're ready. The barometric pressure at the center of a hurricane is often used to measure the strength of the hurricane because it can predict the maximum wind speed of the storm. A scatter plot shows the relationship is straight, strong, and negative. As we learned in chapter 6, we're talking about the direction, the form, and the strength, which we're referring to here, correlation. It has a correlation of negative 0.898. Remember, a correlation measures the strength and direction of a linear association between two quantitative variables. So this is telling me that the direction is negative, which we can see it is. As central pressure increases, the maximum wind speed in knots decreases. It also shows us the strength. So that's a very strong correlation or relationship between central pressure and maximum wind speed. Here is our linear model. So this is our least squares regression model. We want to interpret the model, okay? And what does the slope mean in this context? Does the intercept have a meaningful interpretation and justify our answer? Okay, so what we can notice here is we've got our slope, which is negative 0.972. So let's talk about that first. First of all, it's negative. Okay, so that tells us that the lower central pressure is associated on average with a higher maximum wind speed, right? As we can see, as the central pressure increases, the maximum wind speed starts to decrease. And that's pretty consistent with the way hurricanes work, okay? The slope value says that on average, the maximum wind speed is about negative point, or we should say just 0.972. Okay, I'm not going to use the negative version. That just represents a decrease. It's 0.972 knots higher for every 1 millibar drop in central pressure. That's MB, millibars. So if you recall again, remember slope is change in y over change in x. And I know y is maximum wind speed. And I know x is central pressure. So all I did was relate the negative 0.972 to the maximum wind speed and central pressure. And the negative just represents a decrease. So if I want, I can take that negative and I can move it down here. It doesn't matter, right? The fraction is still negative. This is just showing me here that the maximum wind speed is 0.972 knots higher for every 1 millibar decrease in central pressure. Okay, that makes more sense. And then I also need to interpret the y-intercept, which is your B0. And the y-intercept here is 1028.18. And by the way, that little hat should go there, not here. Okay, that's a typo. So what we can say about that is the intercept, remember the y-intercept is when x equals 0. So in other words, if the central pressure was 0 millibars, right? That doesn't make much sense. That would be like if it was a vacuum. So if you've studied those in physics, it's basically just instead look at it as a starting point. So the intercept, if the central pressure was 0 millibars, okay, which can't exist because it would be a vacuum, so therefore it's not meaningful. So the intercept is not meaningful because if central pressure, which again is x, is 0 millibars, then it would be a vacuum. Okay, it's just a starting point. Okay, you can pause the video again, and then there are these questions here, A through D, related back to this equation. So you're going to practice interpreting the slope and the y-intercept, and then answering question D. Okay, and then you can unpause when you're ready. Recall the earlier problem about the relationship between price in dollars and house size in square feet in Saratoga, New York. Here's the regression model. You've got price hat equals 8,400 plus 88.67 size. What is the slope and what are its units? So the slope here, we know, is 88.67, and it would be measured in dollars per square foot because, again, slope is change in y, which is price in dollars, over change in x, which is size measured in square feet. So dollars per square foot. What is the interpretation of the slope? Well, the model suggests that house prices average about $88.67 higher per additional 1 square foot of size. You know, you could also suggest that a house price would cost on average about $88.67 more per additional 1 square foot of size. Is the model's intercept meaningful? So our intercept is 8,400. Remember, that would be if the x was 0, and x here is size. So you're basically saying if you had a 0 square foot house, the base cost would be $8,400. Well, no one wants a 0 foot square house, right? So no, it's not meaningful. Your house is 1,000 square feet larger than your neighbor's. How much more is its estimate worth price based on this linear model? So if it's 1,000 square foot larger, I know it's $88.67 per square foot, and I've got 1,000 of them larger. So if I multiply that, I get $88,670. So an increase in home size of 1,000 square feet is associated with an increase in price of $88,670 on average. We're going to stop right there for this video. Please join me in the next video where we're going to look at more at models, but we're also going to look at residuals and what they tell us. Have a great day, everyone.